On May 11, 2025, China achieved a remarkable milestone in transportation technology with the successful demonstration of the world's fastest maglev train reaching a record speed of 621 miles per hour, 1,000 kilometers per hour during tests conducted in Shanxi province. This groundbreaking event marks a significant leap forward in high-speed rail technology, showcasing the integration of advanced aerospace science with rail systems. Key developments and testing. The demonstration test was a pivotal moment for China's Maglev project, confirming the train's ability to navigate effectively, maintain stable suspension, and ensure safe stopping. Conducted in a low-vacuum tube environment, the test significantly reduced air resistance, enabling the train to achieve its unprecedented speed. State media reports, including articles from Xinhua, noted that all systems functioned as expected, with the train's trajectory aligning perfectly with theoretical predictions. The Maglev train utilizes high-temperature superconducting HTS technology, allowing it to levitate above the tracks using powerful magnetic fields. This innovation eliminates friction and noise, enhancing both speed and comfort. The superconducting magnets are cooled to extremely low temperatures, amplifying the magnetic field necessary for levitation and propulsion. The latest iteration of the Maglev system builds on previous prototypes, including one unveiled in Chengdu in 2021 that could reach speeds of 385 miles per hour, 620 kilometers per hour. This current project is a collaborative effort between the China Aerospace Science and Industry Corporation and North University of China, reflecting a comprehensive approach to developing next-generation transportation infrastructure. Implications for travel. The potential commercialization of the Maglev train presents profound implications for travel within China. If operational, the train could drastically cut travel times for long-distance journeys. For example, the trip from Beijing to Shanghai could be reduced to approximately 1.5 hours, compared to the current 5-hour duration using traditional high-speed rail. This efficiency positions the Maglev train as a formidable competitor to air travel, which often involves additional time for airport logistics. Environmental considerations play a crucial role in the development of this technology. The Maglev train operates entirely on electricity, offering a cleaner alternative to conventional transportation methods and significantly reducing carbon emissions. This aligns with China's broader goals to peak carbon emissions by 2030 and achieve carbon neutrality by 2060, addressing the nation's growing transport-related pollution. Future prospects. Looking ahead, the Maglev train is a cornerstone of China's comprehensive transportation strategy outlined in its 14th Five-Year Plan 2021 to 2025. This plan emphasizes the need for innovative infrastructure and aims to connect major urban centers with rural areas, enhancing national connectivity. The Maglev technology is expected to play a vital role in this vision, facilitating faster and more efficient travel across the country. While the Maglev system is still in the prototype phase, there are ambitions for it to be operational within the next 3 to 10 years. This timeline reflects ongoing advancements in technology and the necessary preparations for infrastructure readiness. Comparative insights. Analysis from various sources highlights the significance of China's Maglev train achievement while presenting differing emphases on its implications. For instance, one source focuses on the technical success of the recent tests, while another emphasizes the transformative potential for land travel and environmental benefits. A third source discusses the implications for reducing travel times and enhancing connectivity, albeit with a more cautious perspective on commercialization timelines. Overall, China's advancements in Maglev technology not only signify a leap in transportation capabilities but also encapsulate a vision for sustainable and efficient travel. This innovation has the potential to reshape the future of domestic transit across vast distances, positioning China at the forefront of high-speed rail technology globally. Conclusion. The unveiling of the world's fastest Maglev train is a testament to China's commitment to pushing the boundaries of transportation technology. By integrating advanced scientific principles with practical applications, this development not only promises to revolutionize travel within China but also sets a benchmark for future innovations in transportation worldwide. As the country continues to invest in this transformative technology, the implications for connectivity, environmental sustainability, and travel efficiency are expected to be profound, marking a new era in high-speed travel. The recent unveiling of China's Maglev train, which achieved a groundbreaking speed of 621 miles per hour 1,000 km/h, showcases several counterintuitive aspects that challenge conventional wisdom about transportation technology and infrastructure development. Here are some key points that highlight this counterintuitive information. 1. Speed versus safety. Traditionally, higher speeds in transportation raise concerns regarding safety and control. However, this Maglev train's design integrates advanced technologies that maintain stable suspension and controlled navigation, allowing it to achieve record speeds without compromising safety. This finding counters the common assumption that speed inherently increases risk. 2. Electric versus air travel. While air travel has been regarded as the fastest means of long-distance transportation, the Maglev train's potential to significantly reduce travel times, e.g. a Beijing to Shanghai trip could be completed in about 1.5 hours, challenges the perception that airplanes are the only viable option for rapid travel over long distances. This redefines the competitive landscape of travel options, suggesting that electric ground transportation can rival or surpass traditional air travel in certain contexts. 3. Environmental impact. It is widely believed that advancements in speed often lead to increased environmental degradation. Yet the Maglev train operates entirely on electricity and is designed to produce zero direct emissions, contrasting with conventional air travel and ground transport that contribute to significant carbon footprints. This highlights a counterintuitive reality that high-speed transportation can be environmentally friendly, aligning with global sustainability goals. For infrastructure investment, the idea that high-speed rail systems require enormous upfront costs and extended timelines for development often discourages investment in such technologies. However, the successful demonstration of the Maglev train in a low-vacuum environment suggests that new methodologies can mitigate these costs and timelines. The integration of aerospace technology with rail systems reflects a novel approach that could make high-speed rail more feasible and attractive for investment. 5. Technology transfer. The assumption that new transportation technologies will take decades to develop and implement is challenged by the rapid advancements seen in this Maglev project. The timeline for commercialization, estimated at 3 to 10 years, demonstrates a capacity for swift technological transition and deployment that contradicts the notion that such innovations require prolonged periods of research and development. 6. Public acceptance. It is often thought that the public is hesitant to embrace new transportation technologies due to safety and reliability concerns. However, the excitement surrounding the Maglev train's capabilities suggests a shift in public perception where faster, quieter, and more efficient modes of travel may be welcomed as viable alternatives. This indicates a potential readiness for public acceptance of revolutionary transport solutions. 7. Urban versus rural connectivity. The expectation that high-speed transportation systems primarily benefit urban centers is challenged by the planned infrastructure development that aims to connect rural areas with cities. This vision not only enhances mobility for underserved regions but also supports balanced regional development, countering the assumption that such technologies would primarily cater to urban populations. 8. Comparative speed metrics. While conventional wisdom may suggest that aircraft are the fastest mode of transport, the Maglev train's speed surpasses that of many commercial airplanes under specific conditions. By operating in a low-vacuum tube, the Maglev minimizes air resistance, showcasing how innovative engineering can redefine speed benchmarks in ground transportation. These counterintuitive insights highlight the potential of China's Maglev train technology to reshape future transportation paradigms, emphasizing that advancements in speed, safety, environmental sustainability, and connectivity can go hand in hand. As this technology progresses towards commercialization, it may fundamentally alter how we perceive and engage with travel on a global scale. The report on China's unveiling of the world's fastest maglev train, which achieved a record speed of 621 miles per hour during tests, contains numerous details that, while significant, may be overlooked by many readers. Below are some key insights and their implications that are crucial to understanding the broader context and potential impact of this technological breakthrough.
1. Low vacuum environment. Significance: the maglev train operated within a low-vacuum tube environment,
which is a critical aspect of its design that enables such high speeds. This technology minimizes air resistance, allowing the train to reach speeds that traditional trains cannot achieve due to friction. Why it's overlooked: many discussions focus on the speed itself, but the low vacuum aspect is vital for understanding how the train can operate without the limitations faced by conventional rail systems. The ability to maintain a low vacuum environment at a grand scale is a significant engineering challenge that reflects advanced technological capabilities.
2. High temperature superconducting HTS technology.
Significance: the use of HTS technology is a major advancement that allows the train to float above the tracks using powerful magnetic fields.
This not only eliminates friction but also reduces noise pollution,
making the system more efficient and environmentally friendly. Why it's overlooked: readers may not grasp the complexities and innovations involved in superconducting technology. The significance of cooling magnets to extreme temperatures and the resultant amplification of their magnetic fields is central to the train's operation, but may be lost in the excitement over speed.
3. Integration of aerospace science.
Significance: the collaboration between the China Aerospace Science and Industry Corporation and North University of China highlights the interdisciplinary approach required for such innovations. This integration of aerospace principles into rail technology not only enhances performance but also reflects a broader trend of cross-industry collaboration in technological development.
Why it's overlooked: the mention of aerospace science may not resonate with readers who are primarily focused on terrestrial transportation.
However, this interdisciplinary partnership underscores the depth of research and innovation that goes into such advancements, indicating that breakthroughs in one field can significantly benefit another. 4. Environmental impact. Significance: the maglev train's operation is entirely electric, positioning it as a cleaner alternative to conventional modes of transport. This aligns with China's environmental goals of peaking carbon emissions by 2030 and achieving carbon neutrality by 2060, making it a potential game changer in reducing transport-related pollution. Why it's overlooked: while sustainability is a common theme in technological discussions, the specific environmental benefits of this maglev system compared to air travel or traditional rail systems may not be fully appreciated.
The potential to significantly reduce emissions and energy consumption is a critical aspect that merits more focus.
5. Transformation of travel times and connectivity. Significance: the potential for a journey from Beijing to Shanghai to be completed in about 1.5 hours could revolutionize travel dynamics within China. This speed would not only enhance efficiency but also promote economic growth by better connecting major urban centers with rural areas.
Why it's overlooked: the implications of reduced travel times on social and economic structures may be underestimated. Enhanced connectivity could reshape regional economies, influence migration patterns, and alter the logistics landscape.
These broader societal impacts may not be immediately evident in discussions focused on speed alone.
6. Commercialization timeline and infrastructure readiness.
Significance: while the technology is currently in the prototype phase, the expectation of operational deployment within the next 3 to 10 years is crucial for stakeholders in transportation infrastructure development and urban planning.
Why it's overlooked: readers may assume that once a prototype is successful, commercialization will follow swiftly.
However, the complexities of infrastructure readiness, regulatory approvals, and public acceptance are significant hurdles that could impact the timeline and implementation of such transformative projects.
7. Global competitive implications.
Significance: China's advancements in maglev technology position it as a leader in high-speed rail innovation, potentially influencing global standards and practices in transportation. This could have geopolitical implications as nations assess their capabilities in transportation technology. Why it's overlooked: the competitive landscape of international transportation may not be front of mind for those focused on domestic advancements. However, understanding China's role in global transportation innovation can provide insights into future trends and competitive advantages in the sector. 8. Addressing transport emissions. Significance: given that China accounted for a significant portion of global transport-related emissions, the introduction of maglev technology can play a crucial role in mitigating these effects. The system's efficiency and low operational emissions are directly aligned with global efforts to combat climate change.
Why it's overlooked: the direct link between transportation technology and climate goals may not be apparent to all readers. Highlighting the environmental urgency of such innovations can foster a deeper appreciation of the maglev train's role in broader climate action efforts. Conclusion: the unveiling of China's maglev train capable of reaching unprecedented speeds is not just a technological marvel but a multifaceted development with far-reaching implications. By focusing on aspects like low-vacuum technology, interdisciplinary collaboration, environmental benefits, and the potential for transforming travel, we gain a fuller understanding of why this achievement is significant beyond its immediate novelty. As discussions around transportation technology evolve, recognizing these intricacies will be crucial for stakeholders across various sectors, including government, industry, and environmental advocacy. The unveiling of China's world's fastest maglev train, which achieved a record speed of 621 miles per hour, 1,000 kilometers per hour, marks a significant advancement in transportation technology. Here are 4 valuable points for in-depth analysis and discussion. 1. Technological innovation and engineering achievement. The successful demonstration of the maglev train showcases a significant engineering feat in transportation technology. Utilizing high-temperature superconducting HTS technology, this train levitates above the tracks using powerful magnetic fields, thereby eliminating friction and enabling unprecedented speeds. The integration of a low-vacuum environment further enhances these capabilities by reducing air resistance, which is critical for achieving such high velocities. This technology not only represents a leap forward in train design but also emphasizes the potential for integrating aerospace science with rail systems. The implications of these advancements can lead to further innovations in various fields, including energy efficiency, noise reduction, and safer transportation methods. 2. Impact on long-distance travel and infrastructure. The potential impact of the maglev train on long-distance travel is profound. For instance, the projected travel time from Beijing to Shanghai could be reduced to approximately 1.5 hours compared to the current 5-hour journey using traditional high-speed rail. This efficiency positions the maglev train as a viable alternative to air travel, which often involves lengthy airport logistics. Furthermore, the maglev project aligns with China's broader transportation strategy as outlined in its 14th Five-Year Plan 2021 to 2025. Which emphasizes the need for innovative infrastructure. The goal is to enhance connectivity between urban centers and rural areas, thereby transforming the transportation landscape and fostering economic development. 3. Environmental considerations and sustainability goals. The environmental benefits of the maglev train are noteworthy as it operates entirely on electricity and generates no direct emissions. This aspect aligns with China's ambitious goals to peak carbon emissions by 2030 and achieve carbon neutrality by 2060. As transportation emissions have surged due to an increase in passenger vehicles, the maglev train presents a cleaner alternative that can significantly reduce the carbon footprint associated with long-distance travel.
The ability to minimize air pollution while providing fast transportation options is vital for addressing climate change and promoting sustainable development. 4. Future prospects and commercialization challenges. While the technology is still in the prototype phase, expectations for operational deployment within the next 3 to 10 years reflect ongoing advancements and the need for further testing and infrastructure readiness. The commercialization timeline is critical as it will determine how quickly this technology can be integrated into the existing transportation network. There are also challenges related to public acceptance, regulatory approvals, and the financial investments required to develop the necessary infrastructure. The potential for transforming travel and connectivity hinges not only on technological readiness but also on overcoming these hurdles to bring the Maglev train into commercial service. In summary, China's advancement in Maglev technology highlights significant engineering achievements, the potential to revolutionize long-distance travel, environmental sustainability, and the complexities of bringing such innovations to market. Each of these points warrants further exploration to understand the broader implications for transportation, the economy, and the environment. 1. The Concorde supersonic jet. The Concorde was a turbojet-powered supersonic passenger airliner that operated from 1976 until 2003. It was developed jointly by British Aircraft Corporation and Aerospace. The Concorde could fly at speeds over 1,350 miles per hour, 2,180 kilometers per hour, significantly reducing travel times across the Atlantic Ocean. For example, a flight from London to New York would take approximately 3.5 hours compared to around 7 to 8 hours for conventional aircraft. The Concorde's operation was marked by its advanced aerodynamics and engineering, similar to how China's Maglev train utilizes cutting-edge technology to achieve unprecedented speeds. 2. The Hyperloop concept. Proposed by Elon Musk in 2013, the Hyperloop is a high-speed transportation system that aims to transport passengers in pods through low-pressure tubes at speeds potentially exceeding 600 miles per hour, 965 kilometers per hour. The concept emphasizes magnetic levitation and reduced air resistance, akin to the low-vacuum environment utilized by China's Maglev train. Various companies are currently working on developing this technology, which could revolutionize ground travel by offering fast, efficient, and environmentally friendly transportation options. 3. The Shinkansen bullet train. Japan's Shinkansen, commonly known as the bullet train, began operations in 1964 and has since become a symbol of high-speed rail travel. The trains can reach speeds of up to 320 kilometers per hour, 199 miles per hour on certain lines. The Shinkansen has transformed travel within Japan, drastically reducing travel times between major cities. Like China's Maglev train, the Shinkansen represents a significant advancement in rail technology, showcasing the importance of efficient transportation networks in modern society. The success of the Shinkansen has influenced high-speed rail developments worldwide, including the advancements seen in China's transportation infrastructure. Future outlook: China's Maglev train revolution. Introduction. China's unveiling of the world's fastest Maglev train, achieving speeds of 621 miles per hour, 1,000 kilometers per hour, represents a pivotal moment in transportation technology. This innovative development promises to reshape travel dynamics within the country and potentially influence global transportation systems. As the Maglev train moves from prototype to operational status, several critical trends and implications will emerge, shaping the future of travel infrastructure and environmental sustainability. Speed and efficiency. The Maglev train's extraordinary speed opens up new avenues for travel efficiency. If commercialized, the time required for long-distance journeys, such as from Beijing to Shanghai, could be reduced to approximately 1.5 hours. This reduction in travel time makes the Maglev train a viable competitor not only to existing high-speed trains but also to air travel. With increasing urbanization and the continuing growth of megacities, such efficient travel solutions will become essential for maintaining economic connectivity and productivity.
Infrastructure development and integration. The successful introduction of Maglev technology will necessitate extensive infrastructure development.
The integration of this new system into China's existing transportation networks will involve constructing low-vacuum tubes, associated stations, and supporting facilities. As part of the country's 14th five-year plan, these developments will aim to enhance connectivity between urban and rural areas, facilitating economic growth and mobility across diverse regions.
Environmental sustainability. The Maglev train's operational model aligns with China's commitment to environmental sustainability. As an electric-powered system, it offers a cleaner alternative to traditional fossil fuel-based transportation methods, significantly reducing carbon emissions. With China's ambitious goals to peak carbon emissions by 2030 and achieve carbon neutrality by 2060, the Maglev train could play a pivotal role in meeting these objectives, addressing the urgent need for sustainable transportation solutions amid rising pollution levels. Economic implications. The commercialization of the Maglev train could provide significant economic benefits.
By facilitating faster and more efficient travel, the system may spur economic activity by improving access to markets, jobs, and services. The reduced travel time could enhance productivity for businesses and individuals alike. Furthermore, the development of this technology could position China as a leader in the global transportation technology market, fostering innovation and attracting international collaboration.
Challenges and considerations. While the prospects for the Maglev train are promising,
several challenges need to be addressed. The technology is still in the prototype phase, and the timeline for operational deployment remains uncertain, with estimates ranging from 3 to 10 years. Additionally, the high costs associated with building the necessary infrastructure may pose significant financial challenges. Ensuring safety and reliability at such high speeds will also be critical, necessitating rigorous testing and regulatory oversight.
Global influence and competition. China's advancements in Maglev technology may spur competition and innovation in other countries.
As nations recognize the potential of high-speed transportation systems, there may be increased investment in similar technologies worldwide. This could lead to a global race for high-speed rail supremacy, encouraging countries to innovate and improve their transportation infrastructures.
Collaboration among nations could also yield shared technological advancements and best practices. Conclusion. The successful development and commercialization of China's Maglev train could mark a turning point in the evolution of transportation, offering unprecedented speed, efficiency, and environmental sustainability. As this technology progresses, it will not only transform domestic travel within China but also influence global transportation trends. The future of travel could very well be shaped by this groundbreaking innovation, leading to a more interconnected and sustainable world.